The topic of today's lecture is the chain rule, which is a rule for differentiating the composition of two or more functions. Previously, we've learned rules for how to differentiate the sum, product, and quotient of two functions. While these rules are fundamental, they do not tell us how to differentiate a broad class of composite functions. Let's see how the chain rule remedies this situation. The chain rule states that if f and g are both differentiable functions, and if h of x is the composition of f and g, namely f of g of x, then h is a differentiable function, and the chain rule asserts that h prime of x is f prime evaluated at g of x times g prime of x. Rephrasing this, if h is the composition of f with g, f is the outer function, g is the inner function, and the derivative of h is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Here's the first example. Given the function h of x is 3 minus 7x to the fifth power, find h prime of x. Here's the solution. Recall the chain rule tells us that h prime of x is f prime of g of x times g prime of x. Here f is the outermost function and g is the innermost function. In our particular example, we see that the outermost function is x to the power of 5, and the innermost function is 3 minus 7x. Computing these derivatives, we see that h prime of x is 5 times the quantity 3 minus 7x to the fourth power times negative 7. 5 times the quantity 3 minus 7x to the fourth power represents the derivative of the outermost function x to the fifth evaluate the innermost function 3 minus 7x times negative 7, which represents the derivative of the innermost function 3 minus 7x. Simplifying, we see the derivative of h at x is negative 35 times the quantity 3 minus 7x to the fourth power. Here's the second example. Given the function h of t is 4t divided by 3t cubed plus 2 all to the third power, find h prime of t. Here's the solution. Recall that the chain rule tells us that the derivative of h of t is the derivative of the outermost function evaluated at the inner function times the derivative of the inner function. In this case, the outermost function is t cubed, and the inner function is 4t divided by 3t cubed plus 2. To find the derivative of the innermost function, we'll need to use the quotient rule. Computing the derivatives, we see that h prime of t is 3 times the quantity 4t divided by 3t cubed plus 2, quantity squared, times 4 times 3t cubed plus 2 minus 4t times 9t squared, all divided by 3t cubed plus 2 quantity squared. Again, we use the quotient rule to compute the derivative of the innermost function. After simplification, we see that h prime of t is equal to 348t squared plus 576t to the fourth minus 1728t to the fifth, all divided by 3t cubed plus 2 to the fourth power. Here's the next example. Given that h of x is f of g of x, find h prime of 6 using the following table of information. Notice that the table gives us two values of x. Either x can be equal to 6 or x can be equal to 36. Then we can find the values of f, g, f prime, and g prime using the table. So, in order to find h prime of 6, we use the chain rule, which says that h prime of 6 is f prime of g of 6 times g prime of 6. According to the table, g of 6 is 36 and g prime of 6 is 12. Entering that information into the formula of the chain rule gives us that h prime of 6 is f prime of 36 times 12. The table also tells us that f prime of 36 is 24. So, putting it together, we see that h prime of 6 is 24 times 12, which is 288. As we have seen, the chain rule tells us that the derivative of a composition of two functions is the derivative of the outer function evaluated at the inner function times the derivative of the inner function. Identifying functions as a composition of two functions can be tricky. If you feel uneasy about this, take some time practicing with composition of functions. As we saw in our first example, the chain rule can be tremendously more effective than the previous differentiation rules. So, let's gather a few remarks before proceeding to further examples using the chain rule. First, we have the Leibniz notation. If y is equal to f of u, and u is equal to g of x, and in particular y is equal to f of g of x, then dy dx is equal to dy du times du dx. Here, dy du represents the derivative of the outermost function, and du dx represents the derivative of the innermost function. A useful trick to remember the chain rule is to think about the two differentials du canceling. However, since differentials can't simply cancel, that's only a trick for remembering how the chain rule works. Secondly, the chain rule can be used to find second derivatives. And recall that the notation for second derivatives is either f double prime of x or d squared y dx squared. Since the chain rule says the derivative of a composite function is the derivative of the outermost function times the innermost function, when computing the second derivative of a composite function, you will need to use the chain rule along with the product rule. Finally, the chain rule can be applied multiple times. So, if f capital of x is little f of g of h of x, then f capital prime of x is little f prime of g of h of x times g prime of h of x times h prime of x. So, we work from the outermost function to the innermost function, computing derivatives along the way. Here's the next example. Find d squared y dx squared if y is equal to the square root of 19 minus 3x. Here, the outermost function is the square root of x, and the innermost function is 19 minus 3x. Here's the solution. D squared y dx squared is the derivative of dy dx. The chain rule tells us that dy dx is negative 3 divided by 2 times the square root of 19 minus 3x. Using the quotient rule, we see that this is 2 times the square root of 19 minus 3x times 0, which is the derivative of negative 3, minus negative 3 times the quantity 2 times negative 3 divided by 2 times the square root of 19 minus 3x, all divided by 2 times the square root of 19 minus 3x quantity squared. Simplifying, we see that d squared y dx squared is negative 9 divided by 4 times 19 minus 3x to the power 3 halves. Let's look at one last example. Given the composite trigonometric function f capital of x is the cosine of e to the power negative x squared plus x, find f capital prime of x. Notice here that the function f capital of x is a composition of three functions: cosine of x, e to the x, and negative x squared plus x. Here's the solution. Recall that the chain rule for the composition of three functions states that f capital prime of x is equal to little f prime of g of h of x times g prime of h of x times h prime of x. Since little f is cosine of x, little g is e to the x, and little h is negative x squared plus x, we can compute these derivatives to see that f capital prime of x is negative sine of e to the negative x squared plus x times e to the negative x squared plus x times negative 2x plus 1. Simplifying this expression, we see that f capital prime of x is equal to the quantity 2x minus 1 times e to the negative x squared plus x times the sine of e to the negative x squared plus x. So, if we see a function inside another function, we differentiate using the chain rule. We need to have a command of the previous differentiation rules, as long as knowing common derivatives, so that we can use the chain rule in conjunction with our other differentiation rules. Take some time to work the practice problems below so that you can get better command of using the chain rule. As you know, practice makes perfect. Thanks for listening, and good luck.